Hello, my name is Emily Krull, and I'm from the Center for Materials and Sensor Characterization at the University of Toledo. This video is for EDS users who already know the basics and are looking for more advanced information to push their quality of characterization to the next level. If you are just starting out with EDS, I would suggest watching the introduction video first so you have a strong base to learn from. I'll provide a link to that video below. Quickly reviewing energy dispersive X-ray spectroscopy, I wanted to remind you that the process starts with the bombardment of a sample with a primary electron beam. This leads to an emission of X-rays from the sample that is then detected and converted to an electrical voltage. From the characteristic X-ray spectrum generated from this electrical signal, elemental analysis can be done. As we went over in the introduction video, there are several factors that affect the signal you get from your sample. First was the working distance, as well as the voltage, spot size, acquisition time, process time, and sample preparation. So far, I've only talked about EDS with respect to scanning electron microscopes, but it's also important to understand that this technique can be applied to transmission microscopes as well. In the SEM, we see that the primary beam hits a very thick sample, but in transmission microscopy, the sample is very thin and the beam actually passes through the sample. While it is still possible to detect the X-rays generated from this kind of sample in a very similar way, having the beam pass through the sample affects EDS in a lot of different ways. Just a few of the most important examples are given on this table. Because of the setup of the stem, you can detect the entire range of X-rays due to the voltage maximum being able to reach almost 300 keV. While transmission microscopes can go as high as 300, it's only realistic to generate X-rays up to 50 keV. Spatial resolution is lower in the SEM due to the scattering of the beam in the comparatively thick sample specimens, as well as the size of the interaction volume, which can be about 2 to 5 microns. But in the thin TEM or STEM samples that are 200 nanometers or thinner, there's less spreading, as well as having a higher incident beam voltage. Therefore, it gives a higher spatial resolution. This also plays a role in it having a lower detection limit than that of the SEMs. However, there is an advantage to having the thicker samples, and that can be seen in the count rates, which are higher in the SEM due to the bulk material. Unfortunately, because of that, the noise can also be higher. Another issue with the thick samples is X-ray absorption. Ideally, when an electron beam is used to excite a sample, the X-rays are admitted and picked up by a detector. When there are very thick samples, there is a possibility that the material itself absorbs the X-ray, and it never actually reaches the detector. This absorption is a function of the depth of the X-rays produced, making thicker samples more susceptible. The ratio between the measured X-ray intensity to the generated X-ray intensity is also dependent on the mass absorption coefficient, specimen density and thickness, as well as the energy used. Low energy peaks were more strongly absorbed than the high energy ones, and that's because the low energy X-rays no longer have sufficient energy to overcome the binding between the electron and the nucleus of the atoms in the sample. When the X-ray energy is greater than that of the binding energy, the probability of absorption reaches a distinct maximum, and this is known as an absorption edge. Looking at the X-ray spectrum, you can identify if and where the absorption edge is by looking for an abrupt decrease in the continuum background. On this spectrum of nickel, you can see an example of the sharp step in the background at its absorption edge, where that red star is. The probability of X-ray absorption can be calculated using Beer's law, where the fraction of X-rays transmitted is a function of the mass absorption coefficient, mu sub m, density, and thickness d. The absorption coefficient is a function of the energy of the X-rays, the composition of the material that the X-rays have to traverse, and the density and thickness of the sample itself. Ideally, what you see in EDS is that there's an X-ray absorbed by a sample atom, which is then left in an excited state. When the atom relaxes, it ends up emitting its own characteristic X-rays. These are known as secondary fluorescence. Because an X-ray can be absorbed only in an interaction with an electron that has a lower energy than itself, the energy of the secondary fluorescence released is less than that of the primary X-ray. However, it's possible that the X-ray fluorescence, also known as secondary X-rays, can be generated from partial energy absorption of the primary X-rays. Let me give you an example of that. If you look at a sample comprised of copper and iron like the one here, the K-alpha radiation from the copper in the sample can affect the iron. Therefore, if an incident electron beam can eject an electron from the copper atom, an electron from a higher energy level will drop in to fill that hole, releasing the K-alpha radiation of 8.04 keV, like we've seen before. But this emitted radiation is of sufficient energy to excite an electron from the K-shell of the iron atom, leading to the release of a K radiation of 7.11 keV that is ultimately the one that is detected. As a consequence, the measured iron intensity would be increased due to the fluorescence by copper, while the copper intensity would be decreased. The fluorescence effect is very dependent on the shape and the thickness of the sample and can cause some serious artifacts in EDS measurements. They affect the spatial resolution and can cause errors, especially when doing quantification, by altering the peak ratios between two elements like the copper and iron you see here. However, this can be minimized if a sufficiently thin sample is used, so the secondary fluorescence is only significant if the characteristic energy is within approximately 3 keV of the critical ionization energy needed to eject the electron. Additionally, the fluorescence effect can be calculated with sufficient accuracy for corrections. Because the absorption, fluorescence effect, and the dependence on the atomic number, it is very complex to relate the peak intensity of a thick SEM sample to a quantifiable value. On the other hand, since the absorption and fluorescence is negligible or easily calculated in the thin transmission samples, it is much more reliable to draw quantification data from the peak intensity. Therefore, in these thin samples, the peak intensity is proportional to the concentration and specimen thickness. Take a look at this spectrum for a sample containing titanium, silica, carbon, and oxygen. By using Beer's law, we can calculate the atomic percent of each element based on the number of counts from this thin sample. The density and thickness are also needed to give good estimation of the concentration because of the absorption and fluorescence effects. You can see on this graph, by assuming the different thicknesses and densities, the calculated concentration of titanium is affected. The actual thickness of the sample was about 150 nanometers and the density was 4.23. Giving a concentration of 12.31%. If the density and thickness were not used to calculate the absorption correction, this value would have been off by 7.41%. Alternatively, if the thickness and density was assumed to be 250 nanometers and 4 respectively, the concentration of the titanium would have been off by 3.42%. This is why it's important to include these parameters when doing quantitative research with transmission microscopes. Unfortunately, absorbance and fluorescence are not the only issues that occurs with EDS. One big source of error is sum peaks. Sum peaks are the result of two X-rays hitting the detector at exactly the same time. Because they hit at the same time, the pulse processor does not register them as individual events, but instead sums the two signals together to form a new peak. For example, you can have the sum peaks in pure samples. This titanium spectrum shows 3 sum peaks. The first sum peak is actually from the two K-alpha events, the second is from K-alpha and K-beta hitting the detector at the same time, and the third is from 2 K-beta signals. Not only can X-ray signals from a single element form sum peaks, but X-rays from multiple elements can also form these peaks. These become a real issue when the sum peaks are in a spectral location that is known to an element. For instance, the sum X-rays from magnesium and calcium are often mistaken for vanadium because the sum peak is in the correct location for where the vanadium would be if it was present. Silica and calcium sum peaks also appear to be chromium, magnesium and potassium forms peaks mistaken for titanium, and the list, unfortunately, goes on and on. The probability of a sum peak forming is proportional to the product of the count rates of the two parent signals. Therefore, many times the sum peaks can be mathematically identified as the size of the sum peak varies as the square of the count rate. Even though modern EDS software can identify a number of sum peaks based on this relationship, it is usually better just to avoid them in the first place. There are a couple of ways to minimize sum peaks. The first is lowering the processing time, and the second is reducing the electron beam intensity. Lowering the beam current lowers the count rate and usually eliminates the problem. Alternatively, the processing time can be decreased, which allows for the pulses to be processed faster. But remember that the processing time is spent reducing noise from the X-ray signal coming from the detector, so you may have more noise. However, you should understand that by making these changes, you will also affect the spectral resolution and the dead time. Take a look at the tables on the right. It shows that when you lower either the current or the processing time, the potential for some peaks is decreased. Unfortunately, in both of these cases, there's also an increase in peak width, meaning that the spectral resolution is worsened. Also note that the dead time is affected as well. Dead time and the potential for some peaks are closely linked. A quick refresher. Dead time is a designated time during which pulses are not measured, and is a tool that's used to minimize pulse pileup in the detector. While dead time decreases pulse pileup, it can also increase the amount of signal that is rejected. You can see here that at a 15% dead time, the some peaks are small compared to the higher dead times. Usually it is considered that a dead time of less than 10% leads to some peaks that are of negligible intensity. On the other hand of the spectrum, when the dead time is over 60%, the data is really not that reliable because so much has been rejected and any some peaks would be noticeably large. In practice, the input count rate of the EDS detector is normally selected that the dead time is below 40% but above 10%. The lower the dead time on the phase ID minimizes the some peaks, while the dead time is slightly higher for trace elements if you wanted to find those, to maximize the output so that you're able to detect the small amounts of the trace elements. The higher the dead time, the more the pulse pileup and the peak distortion becomes an issue. The maximum dead time, therefore, that it can be used is 60%, and that can be used for mapping. Mapping is generally used for qualitative or comparative work rather than quantitative, so spectral artifacts can be more present in that form than others without causing too big of an issue. On top of that, the higher dead time maximizes the output so that the mapping does not take an exorbitant amount of time. A general rule of thumb that can be used to help with the reduction of any sort of mapping is to increase your dead time. Dead time is not only a factor in the presence of some peaks, but can also be correlated to spectral resolution, as I said before. The spectral resolution is measured in the electron volts and is taken as the full width of the peak at half of its maximum. Much like the dead time, it is related to the time constant or process time when collecting the spectrum. The process is the time spent by the pulse processor in measuring the incoming X-ray signals. The longer the process time, the better the resolution will be, and the narrower the peaks, and the lower the noise. In the diagram above, P1 is the shortest processing time, while P6 is the longest. Note that the longer the processing time, the greater the dead times, but the better the resolution. Overall, it is by selecting different processing times that it is possible to reduce differing amounts of noise. When the noise is minimized, the resolution of the peak displayed in the spectrum is improved, and it becomes easier to distinguish between peaks that may be very close in energy. This can be incredibly important. For example, there are 16 common peaks that have energies between 2 and 3 kiloelectron volts. Overlapping happens when the spectral resolution is not good enough to be able to distinguish between peaks that are close together, like the 16 I just listed. This is not the same as a sum peak. A sum peak occurs at the detector and the two energies are summed so that they are placed in a spectral location equal to the sum of the energies. In overlapping, the two signals were detected separately, but put on the spectra at the correct locations for their energies. However, the resolution was not high enough for the two peaks, so they appear as one. This is especially common at lower energies. One reason it's common at lower energies is because there are simply so many energies from common elements present in the lower ranges, as you can see in this figure. But really more than that, there's the possibility of overlap from heavy and light elements. Looking at this figure, you can see that the L energies from the heavier elements overlap with the K lines from the lighter elements. So how do you know if you have overlapping peaks? The first thing to do is to look for peaks that are displaced from its marker. In this case, we can see that the lighter orange overlapping peak that comes from tantalum, silica, and tungsten. If you look closely, the location of this overlapping peak, which I labeled with a black line, is not perfectly aligned with the position of silica or tantalum, so you can see it's just slightly shifted. The next thing to look for is if the relative intensities are wrong. For this example, let's look at the characteristic X-rays of iron. These characteristic wavelengths for iron, as well as the sun peak for the L-alpha and K-alpha wavelengths of iron, have specific relative intensities to each other depending on the beam energy used. If the computer sees that the intensity of the L-alpha line becomes much greater with respect to that of the other characteristic peaks, like this, then it can be assumed that there is an overlapping occurring at the L-alpha wavelength that is causing it to be artificially higher. In this example, the overlap could be from tin, whose M line is only 1/100th of a decimal point off from the iron L-alpha line. Lastly, you want to look and see if there's any distortion in the peak shape. Then there's an overlapping of the element. Looking here at the peak shape of iron in pink, you can see that the overlapping of the chromium and manganese causes the shape to be distorted, and you end up with the gray spectrum. This is a helpful tool for identifying peak overlap in EDS spectrum along with the relative intensities and marker displacement. In practice, you will likely see all three conditions present in an overlapping situation. There are ways that you can correct for overlapping, luckily. The first is to increase the spectral resolution so that the program can differentiate between the peaks that are close together. Like I mentioned before, this can be done by increasing the processing time to a degree and increasing the beam current. If it is not possible to distinguish between them still, a peak deconvolution software or peak stripping may be necessary. This is a mathematical process that allows the analyst to remove the identified peak structures to reveal possibly hidden peaks if they exist. This is what you see in the image. The overlapping peaks in gray was deconvoluted to reveal that there was chromium and manganese present. Neither of these corrections are perfect though, and you should know that some lines and wavelengths are so close together that it could be impossible to make the two separate intensity measurements. This would be known as a problem region. This is where a spectral region where two or more elements produce primary characteristic peaks that are so close in energy that they might both be possible solutions. If you are looking at your spectrum and you find that there are elements present that should not be there, but there's no indication that there's any overlapping or some peaks, it might be due to stray X-rays. These are X-rays produced from the sample holder or other materials in the microscope itself. A lot of times this is due to high energy backscatter electrons generated by the sample hitting something in the microscope that also generates an X-ray. These problems are exacerbated when the sample is rough. If you are analyzing a part of a sample near an edge, or if your working distance is not correct, it will also be worse. Especially when running EDS with a TEM or STEM, it is important to understand where these stray electrons are coming from. I say it's particularly important for TEM because the TEM routinely sits on grids that have high energy electrons that go through the specimen and could hit part of the column or the chamber, which results in these stray X-rays finding their way back to the detector. Here's a list of some possible elements and their sources for these stray X-rays. You should look at this as a guideline and not a set of elements that will always pop up, because there's not always going to be a strong enough signal from these X-rays to overcome the background noise. On top of that, not every microscope is going to be made with the same exact materials. As if the some peaks, overlapping, and stray X-rays weren't enough of a headache, another source of error in EDS is escape peaks. To understand escape peaks, you first have to understand how the detector for EDS works. Here's a very basic diagram of one type of detector and its parts. First is the collimator, which helps block any stray X-rays that were not produced from the area of interest. The electron trap following is meant to keep electrons from entering the detector, only allowing X-rays to pass through. The window, which is usually either a beryllium or a polymer, allows for the vacuum to be maintained while supporting the transmission of photons to the crystal. Some detectors do not have a window, just so you know. The crystal itself is a silica semiconductor, And lastly on this diagram is the File effect transistor, which converts the pulse from the crystal to a voltage pulse that can be used to generate the spectrum. While all these parts are important, it's the silica crystal that we're mostly interested in regards to escape peaks. The detector for the EDS typically has a silicon crystal. Much like how the incident beam knocks electrons out of the shell for the sample, an X-ray that is hitting the detector can generate an electron-hole pair. For a silica detector, it takes around 3.8 eV to generate the electron-hole pair needed. Because the electrons are negative and there is a bias voltage generated across the detector, the electrons and the holes move towards the positive charge maintained at one side. This movement generates a charged signal. For an incoming nickel K-alpha X-ray energy of 7.477 keV, 1,968 electron-hole pairs will be produced. For an aluminum K-alpha X-ray of 1.487 keV, 391 electron-hole pairs will be generated. So the number of electron-hole pairs will depend on the energy of the incoming X-ray, and this is what allows us to generate characteristic X-rays from our characteristic signals or peaks from individual elements. To minimize the electronic noise, the detector must also be cooled. These silica detectors cooled here are cooled with liquid nitrogen. But the escape peaks are produced when not all of the energy of an incoming X-ray is converted to an electron-hole pair. When this occurs, the silica K-alpha X-ray is generated from the silicon detector crystal and escapes. Thus, the total number of electron-hole pairs created in the detector changes, creating an energy loss. The resulting energy measured for the incoming X-ray is therefore reduced by the magnitude of the silica K-alpha X-ray, i.e. 1.74 keV. An escape peak is then detected in the ED spectrum. Luckily, less than 2% of incoming X-rays will fluoresce silica K-alpha X-rays, so the escape peaks will only form a Meyer peak that is located at the energy of 1.74 keV, less than that of the energy related to the major peaks of the spectrum. You may be wondering what happens if the generated silica X-rays do not escape. This does happen and can typically start when there is a quote dead region in the silica crystal. This dead region can no longer produce electron-hole pairs, but it can generate X-rays. When the incoming signal hits this region and generates X-rays, some of those X-rays may actually travel to the live part of the detector of the crystal. Because of this, a small silica peak may be visible in your spectrum, even though there isn't any in your sample. Where does the signal that is generated by the crystal go? Well, it goes to the pulse processor, which averages the income signal to reduce the noise. The user has the option to change the amount of time that is spent on averaging process by adjusting the processing time. The longer the processing time, the better the resolution. Be sure to consider your application when adjusting the processing time, though. For applications where maximizing the number of X-rays is important, like in mapping, you may want a lower processing time. But for applications like quantitative analysis, where resolution is very important, you may want a longer processing time. You should know that when you increase the processing time, though, you also increase the dead time. If you're not familiar with the processing time or dead time, I suggest you go back and watch the intro video to EDS, available on the CMSE YouTube page. If you haven't already watched that video or worked with EDS before, you know that counts can really affect dead time, and it affects how good of a signal you can get. If you have a really high count number, then it is possible that the pulse processor cannot differentiate between two incoming X-rays, and that when that happens, both of them are rejected. If the dead time were to reach 100%, then no X-rays are processed at all by the pulse processor, and the detector is said to be flooded. Another thing to be concerned about is the chance of some peaks, which occur when two X-rays hit the detector at the same time, as we mentioned before, and the pulse processor will record the sum of the two peaks. For silicon detectors, it's a good benchmark to aim for count rates about 5,000 to 20,000 and dead times of about 20 to 30%. So far, we've only discussed what happens when characteristic X-rays are generated by the electron beam, but it's important to consider the effects of Bremsstrahlung X-rays as well. Unlike characteristic X-rays like you see here, which are produced by an electron drop from a higher energy shell to a lower one to fill a hole left by an accelerated electron, knocking out another one. The Bremsstrahlung X-rays do not interact with the electron cells, but instead interact with the nucleus. Bremsstrahlung, which translated from German means breaking radiation, which is actually a very good description of what's going on, occurs when an accelerated electron interacts with the nucleus and it is effectively slowed down. The loss of this energy is compensated by the release of X-rays, which is equal energy value to that lost when the electron interacts with the nucleus. The closer the electron gets to the nucleus, the stronger the interaction is. These type of X-rays are also known as continuous X-rays. They're known as continuous because they form a continuous distribution like you can see in these graphs as the orange dotted lines. While they are continuous, the detector has a difficult time with the extremely low generated X-rays, low energy, so it appears like the broad blue hump you see instead. These continuum or Bremsstrahlung X-rays are quite a nuisance. They make up the background noise that you would see in the EDS, like that, and thusly determine the minimum concentration of any given element in a sample that is detectable, meaning that if the concentration of an element of interest is not high enough to generate the characteristic peak greater than the Bremsstrahlung background, like there isn't in the top image, then it won't be detectable. Usually to get a characteristic peak that is detectable, like in the bottom image, the concentration needs to be a minimum of 1000 ppm or 0.1 weight%. This is just used as a guideline as the intensity of the background can increase with changes in the probe current, atomic number, and accelerating voltage. It should also be noted that regardless, it is usually considered that there is an error of plus or minus 1% 1 to 2% when running quantitative EDS. One last interesting point is that when there are zero X-rays produced via Bremsstrahlung interactions, this is called the Dwan-Hunt limit, which you see in purple. To really understand the detection limits of EDS, one has to look at the peak-to-background ratio. The formula for the peak-to-background ratio is as follows, where the variables stand for the critical ionization energy, accelerating voltage, the atomic number, and the constant for a particular energy in its shell, a particular element in its shell. And that constant n is usually between 1.5 and 2. You would use this equation if perhaps you were not seeing an element you thought you would have, and you wanted to check to see if it was below the detection limit. It's also useful for setting up your analysis for success when you choose the parameters that you're working for. I will caution you though, while it seems like the best peak to background ratio based on this equation would occur at the highest accelerating voltage, you still need to consider that increasing your accelerating voltages decreases the spatial resolution and increases the X-ray absorption. Therefore, it's a good rule of thumb to use an overvoltage of 1.5 to about 3, with the overvoltage being the multiple of the minimum voltage needed to kick the electron out of its desired shell. To add to the tables I showed you earlier, you can see how adjusting the current can affect the counts and the peak-to-background ratio, as well as how the processing time can affect the counts. The processing time will not have a greatly pronounced effect on the peak-to-background ratio. Another parameter we did not see on this table but is important is the acquisition time, which is the total amount of time the system takes to collect the data, not including the dead time. When the acquisition time is increased, you will most notably see the effect in the counts, which will also increase. One other important parameter to mention is spot size. The spot size should be set at the beginning of any analysis session when optimizing parameters. The goal when adjusting the spot size is to make it large enough to generate sufficient X-rays without damaging the sample. Furthermore, because the spot size will also affect the dead time, it should also be set so the dead time is somewhere between 15 and 60%, depending on the application you are doing, like we talked about earlier in the video. Don't forget that in the STEM operation mode, the aperture and the mode is closely related to the spot size. For STEMs, like the Hitachi 2300 that we have here at CMSC, you want to select an aperture size of about 2 to 3 depending on the thickness of your sample, as well as a normal or high resolution operating mode. You should know that the high resolution mode, you will get higher intensity than the normal mode, but at the cost of having decreased spatial resolution. Lastly, in the stem, you can tilt the sample slightly towards the EDS detector to potentially increase the signal intensity from the sample. But this should be done with great caution, for depending on the variability of the thickness and the sample location on the grid, this could also do the exact opposite and decrease the intensity of the signal. Thank you for watching this video. I hope you enjoyed it and found it informative. And good luck with your future EDS analysis.